we're going to look at chemical equilibrium. Equilibrium is defined as the state where the concentrations of all reactants and products remain constant with time. So for an example, you have two island cities connected by a bridge. The total number of cars does not change. They're either on one of the cities or they're in the other city. So when the rate of the forward reaction equals the rate of the reverse reaction, equilibrium has been reached. So again, it's the rate of the forward reaction equals the rate of the reverse reaction. So we're going to use an equilibrium constant, an uppercase K. It's based on the law of mass action. So we have a reaction where we have J number of A atoms plus K number of B atoms goes to L number of C atoms and M number of D atoms. So the equilibrium expression is always going to be the products on top and the reactants on the bottom. So these brackets mean concentration. So we're talking about the concentration of the products over the concentration of the reactants. So let's start with the products. Our products are here. So you notice that this L was the number of C atoms, and this L becomes our exponent. This M becomes our exponent. And then we have our products over our reactants. So this J was our exponent, and this K becomes our exponent. So the coefficients become exponents. This means you need to be able to balance equations because you're going to be using the coefficients in your balanced equations to become exponents. So you absolutely must have the proper balanced equations. And then also notice that we are not going to use units. So we do not care about the units. But let's look and see what this means. So a value of KEQ is much greater than 1 means that at equilibrium, the reaction system will be consisting mostly of products. So the equilibrium lies to the right. So it's really important for you to understand what these values mean. So again, we're saying KEQ is much greater than 1. So the products lies to the right. So the equilibrium lies to the right. So if in this case our KEQ was much greater than 1, we would have our product arrow would be much larger than our reverse arrow. So let's look at a process. And the process that we're going to look at is called the Haber process. So the Haber process is giving us some numbers. Yeah, okay. And we're given a temperature. The temperature in this case is meaningless. You don't need it. But we have some values. We have the value of ammonia concentration, the value of hydrogen concentration, and the value of nitrogen concentration. We also were given the reaction for the Haber process. Nitrogen gas plus 3 hydrogen gas in equilibrium with 2 ammonia gas. So first, what you want to do is set up your KEQ expression. So that would be products over reactants. And then we take our coefficient for the ammonia, and that becomes our exponent. And then our coefficient for the hydrogen also becomes an exponent. And then here we have 1 nitrogen, so we don't put anything here. So once we have our KEQ expression, then all we need to do is plug in the numbers and solve for the value. So we plug in the numbers. Again, we do not use the molarity. We don't use the units. We do the math. And in this case, we get KEQ equals 3.8 times 10 to the power of 4. That is much greater than 1. That means equilibrium lies this way. So looking at another problem, we are given a question asking us to write the equilibrium constant and determine the value. And this is for catalytic methanation. We're given the equilibrium values. And so again, we use a balanced equation, which in this case is carbon monoxide plus hydrogen gas in equilibrium with methane and water. So this reaction is the catalytic methanation. So we set up our expression first, and notice that we have our products here on top over our reactants here. We have a 3 for the hydrogen. That becomes an exponent. We plug in our values, we do the math, and we get a KEQ of 3.93.